Okay, so here's an example of a kinematics problem that involves acceleration versus time graph. Alright, so here we have a car initially moving at a rate of 5 meters per second. It accelerates along a straight line or straight road for 10 seconds, as shown in the schematic, and the acceleration time graph shown below. Okay, it says if the car's initial position at time equal to 0 is negative 12 meters, find the following. Part A asks us to find the instantaneous velocity. Part B asks us also to find the instantaneous velocity. C, average speed, and then D, the car's position at 3.8 seconds. All right, so let's do it. So here, the schematic shows that the car is initially moving at a rate of 5 meters per second, as indicated by that green arrow. It accelerates to the right here, aka speeding up. Its initial position in this particular problem is negative 12 meters. So here, it's important to note that the initial position is not 0. Okay, so not every problem has to start at 0. Here, it starts at negative 12 meters. So to the left of the number line, and it's going to move to the right. All right, the acceleration time graph here gives us that the acceleration is uniform or a constant 2 meters per second square, because this purple line is just a straight horizontal line that indicates that the acceleration stays constant. Not the velocity, but the acceleration. The rate of change in velocity stays constant. All right, so let's knock out these different parts. Part A and B asks us to find the instantaneous velocity, except at two different times, at 2 seconds and 5 seconds. So let's knock out the first one, part A. The easiest way I think to do this would be just to use your VF function. VF is equal to A change in time plus VI. We know A, we know change in time, we know VI, so all quantities are given to us. The acceleration is 2 from the graph itself. Change in time here is 2 seconds because I'm going from 0 to 2 seconds. But if I start my problem from 0 second, then my VI is 5 meters per second as indicated in the schematic. Okay, so if you do that, 2 times 2 is 4, 4 plus 5 is 9, so the answer is just 9 meters per second. But since it asks for velocity, and according to the diagram, the car is going to the right, so make sure you include the direction, unless it uses the word magnitude. All right, the other way to do it is to use the information in the acceleration versus time graph. There's one important piece of information that you can pull from an acceleration versus time graph, and that is the area. Okay, the area for the part A here, because it says from 0 to 2 seconds. So here I've shaded from 0 to 2 seconds all the way up to where the graph is, which is at 2. I can find this area. Now, this particular area tells you the change in velocity. But it's important to interpret this information correctly. The area only tells you the change in velocity. It tells you how much the object has sped up by or slowed down by. It doesn't give you the final velocity, nor does it give you the initial velocity from the area. Okay, but you can use this information to find VF and VI, which I'm going to show you how to do. All right, so if we can find this area real quick, this area is a rectangle, so it's just simply base times height. The base here is 2. The height is also 2, so 2 times 2 is just 4 meters per second. So therefore, we can now substitute it back in here, and then this function, delta V is equal to VF minus VI. Well, delta V we just found as 4 meters per second. VF is my unknown. The negative sign is part of the function, and then my VI is a positive 5 meters per second. So therefore, to solve for VF, I want to add 5 to both sides to get rid of the negative 5. So as you can see here, 4 plus 5 is 9, which is consistent with what we got. Okay, so that gives you the same magnitude. So whichever strategy you like, go for it. Let's do part B. Part B, same process here. Okay, except all we have to do is replace the time because it wants it at 5 seconds. So I'm going to go ahead and use my VF function again. A is 2. My delta t is 5 seconds. My VI is 5. My delta t here again is 5 because I'm starting at 0. At 0 seconds, the object's already moving at a rate of 5 meters per second. Okay, so don't get into a habit of plugging VI as 0. Always read the problem. Make sure your VI fits what's given to you. In this case, the object is already moving, aka the car's already moving when you start this problem. All right, so therefore 2 times 5 is 10, and then 10 plus 5 is 15. So therefore the answer is simply 15 meters per second east. All right, now if you want to use the information from the acceleration time graph here, it wants it at 5 seconds. So I'm just going to shade from 0 all the way to 5. This is about 5. I did my best here to kind of cut off at 5. Okay. And if you go all the way up to the acceleration graph, which is at 2, you notice here it just gives us a rectangle again. So the area of this would just be 5, which is the base, times the height, which is 2. So the area would just be 10. So delta V here in this case would simply be 10 meters per second. VF is unknown, and our VI is 5 again, because that's what it is for this problem. At times equal to 0, and then to solve for VF, you add 5 to both sides, so therefore 10 plus 5 is 15, which is what we got using the VF function. Okay, so if you like to use the area for an acceleration time graph, go for it. I think it's pretty useful, but if you don't know how to find area properly, then you might just use the kinematics functions and just be safe about it. Let's do part C. Part C asks us to find the average speed during the 3rd second. So here's the wording could get the best of you. The 3rd second starts at 2 seconds and ends at 3 seconds. Okay, so listen well here. From 0 to 1 second in physics is known as the 1st second. From 1 to 2 seconds is known as the 2nd second. From 2 to 3 seconds, it is known as the 3rd second. So when this type of language is used, you have to know how to interpret this. Otherwise, kids who are new, you might go from 0 to 3, which is not the case. The 3rd second suggests that the problem starts at 2 seconds and it ends at 3 seconds, which is a 1 second interval. All right, so listen to that again if you need to. All right, so let's do it. To find average speed during this 3rd second, okay, you need to know distance and time, but I don't know what the distance is, but I can find it though real quick. Okay, sorry, that animation came out over there. That 10 is going to be it's going to be proven here. I can use delta x equals VIT plus 1/2 AT squared. You notice here I have VI highlighted because VI is not 5. Okay, VI is not 5. Even though the schematic tells you VI is 5, this VI is 5 when time is equal to 0. But here, the wording tells us that we need to start our problem at 2 seconds. At 2 seconds, though, your velocity is 9 because, well, if VI is 5 and acceleration is 2, every second it increases by 2. So therefore, it's going to go from 5 to 7, which is 1 second. And then 7 to 9, which is another second, which is 2 seconds. So if I'm going to start this particular problem, it starts at 2 seconds. And at 2 seconds, my velocity is 9 meters per second. Okay, do not pull a rookie move and put in VI as 5. VI is 5 only at 0 second, which is not this problem. So VI is 9. T is just 1 because the interval is from 2 seconds to 3 seconds, which is known as the 3rd second. So therefore, from 2 to 3 seconds is just 1 second. All right, so that's where the 1 comes from. The A is from the graph, and then T here is just 1. So if you simplify all that, you should get 10, because 9 times 1 is 9. The 1/2 and the 2 here cancels out. If you watch my cursor, 1 squared is just 1. So 9 times 1 is 9, plus 1 is 10. So that's where this numerator comes from. Okay, so how far did this car travel? It traveled 10 meters to the right during this 1 second window, from 2 seconds to 3 seconds. All right, if you do that and you simplify it, 10 over 1 is just 10. So the answer is just 10 meters per second. Speed is a scalar, so no need for direction here. Okay, now let's go ahead and use the average velocity function if you like. But you notice here, I put the absolute value around it because you can use this function to find average speed. You just have to know not to include the direction in your answer. But to use this function, you have to know 2 quantities, a final velocity and an initial. Well, what's my final, what's my initial? Well, if you kept up with the work on the left side here, my initial velocity for this particular part is 9 because it starts at 2 seconds. So if you didn't know how to get 9 there by reasoning, hopefully watch the work on the right side of the screen. Well, here I have every bullet here that tells you how fast the object is moving at each time. At 0 second, it's at 5 because it's already started moving. At 1 second, it goes to 7 because the acceleration is 2 meters per second squared. That tells you your velocity changes by 2 every second. So it's going to go from 5 meters per second to 7 meters per second. That takes me to 1 second. Well, from 1 to 2 seconds is also going to get faster by a rate of 2 meters per second. So therefore, it's going to go from 7 to 9. Okay, so that's where the 9 comes from. This problem starts at 2, and my VI would be 9 meters per second. But here, if I'm going to use a strategy, I need to know what VF is. Well, if listened to the explanation thus far, the third second implies you start at 2 seconds and you end at 3. So your initial is at 2 seconds, your final is at 3 seconds. So my work on the screen here stops at 3 seconds for that reason. So therefore, I want to highlight 2 seconds. I'm also going to highlight the velocity at 3 seconds, and I can just add those two velocities. So my final velocity is 11 meters per second. My initial is 9 meters per second. 11 plus 9 is 20. 20 divided by 2, which is 10. So therefore, I get the same answer. Average speed during this 1 second interval from 2 to 3 seconds is 10 meters per second, which is what I'm also getting here. So hopefully practice whichever strategy you like, stick with it. I like the right side because it prevents a lot of errors. I think it's easy to write all these bullets for your velocities down simply by adding or subtracting based on whether the object is accelerating or decelerating. So I think it's a little harder to mess up with these bullets. And then once you figure out which time you need, it's easy to add and then divide by 2. Okay, so my preference is on the right side of the screen. All right, part D. It says the car's position at 3.8 seconds. Okay. I do want to point out here that it asks for the car's position, not displacement. Okay. So really it's asking for XF. In the diagram, it shows that the car starts initially at an XI of negative 12 and it's gonna move to the right. So at 3.8 seconds, if I were to take a snapshot of it on the number line, where would this car be located? At what point? Okay. So it's not asking for displacement. It's not asking for distance. It's asking for at which location, a single point on the number line at 3.8 seconds. All right, so let's do it. So I'm going to use my displacement function. Now, why would I do that? Because I know XF is hidden in delta X. Okay, so delta X is usually condensed, but in this case, I'm going to break up delta X. Why? Because I need to find XF. XF is X of T. So therefore, I want to break up delta X into XF minus XI. My unknown is XF here, and that's what I'm trying to find. Well, I have everything already. VI, I know. T, I know. A, I know. And then XI is given as negative 12. So you have to be careful with your algebra here or your substitution. XI itself is a negative value, and then the operation itself here is a negative. So make sure you use parentheses. It'll prevent a lot of mistakes from happening, okay? So here, I have XF, which is I carry down, minus, which is from the function itself, but XI itself is a negative value. So I will encourage you to use parentheses, because if you don't, you can screw up your math here. And then 5 is substitute for VI. My T here is 3.8 seconds. A is given in the graph from the previous 3 parts. And then here T is 3.8 seconds again. And then don't forget to square the second term here. All right, so if you do that, this negative and negative makes it a positive, but then to move a positive 12 to the right side of the equal sign, that changes sign, it will be now negative. So if you simplify all this work on the right, you should get a value of 33.44, and then I'm going to subtract 12. Okay, again, the negative and the negative makes this quantity positive. But in order to get rid of a positive number, you move it to the other side, which changes the sign, which now becomes negative. So if you take 33.44 minus 12, you'll get a value of 21.44. So this is where the object is located on the number line. Again, it's not the distance traveled, it's not the displacement. It is a single point. Okay, so it starts at negative 12, and then somewhere down the line, if I took a picture of it, x of t would equal 21.44. All right. Therefore, that's the answer. Okay. Now, if you like, okay, here's a graph that I have for you. Okay, but I'm going to go ahead and use decimals real quick, and then hopefully teach you how to do this using decimals. Okay. If I can decimals. Okay. Now, in order to kind of graph this, all you need to do is graph the velocity function. I know VF, okay, so VF is AT plus VI. So we need to write that down. So VF is AT, but I know A is 2. And T in decimals is, instead of T, we just use X as a variable. And I want to put plus 5, okay. Now, so that's my velocity function, 2t plus 5. But instead of using t, decimals graphs it with respect to the variable x, which is okay. And then what I need to do is I need to trace out this line where it goes to 3.8. So you see here, I need to find exactly where 3.8 is. And it's not that hard to do if you know how to use a graphing calculator. There we go. So here, the first number is 3.8, which is my time. I'm stopping at 3.8 because the question asked me for 3.8 seconds. But at 3.8, my y coordinate is 12.6. Okay, so you need to keep this in mind. Write it down if you need to. Otherwise, you might forget by the time I close this out. I'm stopping at 3.8 because the problem wants the position at 3.8 seconds. And then the 12.6 tells me the vertical intersection there. Okay, so the coordinate here is 3.6 and 12.6. All right, so if you kept up with that part, therefore it's super easy to do this with you. Okay. All right, so here I just copy and paste the velocity time graph using Desmos. And here I kind of wrote 3.8 here just to keep you focused because part D asks you to find 3.8. Here you can use the area underneath the velocity time graph. The area underneath the velocity time graph tells you your displacement, your delta x. But here, everything is above the t-axis. Like this whole entire diagonal is above the t-axis, which means the car is moving to the right because all the area will be positive. So if I calculate this correctly, this little area right here, which is base times height, my base is 3.8 because I'm going from 0 second to 3.8 seconds. And then my height is 5 because my y-intercept here is 5. Well, why? Because my initial velocity is 5. So if I find this area correctly, it'll be base times height, which is 3.8 seconds. My height is 5 meters per second. And if you multiply that out, you'll get 19 meters, okay? And then we're not done yet though, right? We got to shade all the way from the t-axis all the way up to the line. Well, if you kept up with the Desmos graphing, okay, here I've only gone up to 5, but my coordinate up here was 3.8 and 12.6. So for the vertical axis, I've already used a 5, so the remaining vertical distance is 7.6. Hence, I'm going to use the area of a triangle, a right triangle, which is 1/2 times the base. My base here is the same because I'm going from 0 second to 3.8 seconds. And the 7.6 comes from the leftover. Okay, so I want to say, watch my cursor. Desmos told me if I start from the bottom and go all the way up, it rises 12.6. But I already found the first area, which is a height of 5. So therefore, 12.6 minus 5 gives me 7.6. So if I find the area of a right triangle, which is the remaining area shaded, I get 1/2 times 3.8 times 7.6, which gives me a value of 14.44. Okay. Now, what do you do with that? The area, the total area, represents your displacement, delta x. Well, 19, which is positive because it's above the t-axis. This area for the right triangle is also above the t-axis. So I'm just going to add these two values. So 19 plus 14.44 will give me a value of 13.44. So I like to point out, you see there's a pattern here. You know, there's 33.44. If you do the same strategy, you also get 13.44. XF is what we're trying to find, aka the position at 3.8 seconds, minus XI. I want to carry the operation minus down. I want to substitute XI using parentheses because XI in this particular problem is a negative value. So have good habits, it'll pay off. Okay, so therefore XI is negative 12, but as you can see again, a negative times a negative here will make it a positive. So therefore, we have 33.44 equals XF plus 12, but then to get XF by itself, I need to get this plus 12 to the left side of the equation. So I'm just going to subtract it. So therefore 33.44 minus 12. So if you notice here, this line is the same as this work right here on the left side, 33.44 minus 12. So I'm just going to tell you that you should get the same answer of 21.44. All right. Other than that, I hope that helps. If you like using area, go for it. I think it's pretty useful if you can count and just make sure you find the area, you know, of a rectangle or a right triangle properly. Okay. Stay nerdy. Don't be whack.